hurt, but that formula in calculus is written as y is equal to EKT, whereas K is known as a proportionality constant. But they're all the same. Okay, you can write it like this in a continuous compound interest, or this is a continuous growth or decay formula. Okay, let's start with compound interest. It's a series. Okay, so suppose you put money in a bank, and let's suppose you get 10% interest. Okay, let's say you are going to put in $100, and you're going to put 10% in. You're going to get 10% interest each year. So at the end of the first year, you're going to have your $100 plus 10% of $100, which will be 100 times 0.1. And then that's going to turn into $100 plus $10, which is $110. And at the end of the second year, you're going to still have $110, plus you're going to earn interest on $110. You're going to earn 10% interest, which means times, let's put some brackets around there, times 0.1, which is going to give me $110 plus 10% of that, which is $11, and that's going to give us a total of $121. Okay, so as you keep going, you're going to keep earning interest on what you have already. So what happens if you go like 10 years, okay, or 20 years? Okay, we want to come up with a formula that easy to use rather than trying to calculate this 1 year at a time. And here we go. So the amount of money you're going to have at the end of the first year is going to be the principal, which means the money you're going to put in, plus the principal, the money you put in, times the rate, which is the percentage of interest you're going to get. Of course, this simplifies to, this is the end of the first year, and this simplifies to P times 1 plus R. Okay, so at the end of the second year, you're going to have P times 1 plus R, okay, plus you're going to earn interest on this, so that will be P times 1 plus R times R. Now if you notice, this and this, okay, can be factored out, so let's factor it out. So P times 1 plus R can be factored out. That will leave us in the bracket, in the first one to be 1, and then in the second half I'm going to have A plus R, which simplifies to P times 1 plus R to the second. Now, at the end of the second year, you're going to have P times 1 plus R to the second. At the end of the first year, you're going to have P times 1 plus R to the first. So obviously, if we keep going, you're going to, at the end of third year, you're going to have P times 1 plus R to the third, so on and so forth. And at the end of the nth year, A sub n, we're going to have P times 1 plus R to the n. And this is known as a compound interest formula. So, let's suppose you put in $10,000. And let's suppose you're going to get interest rate of 5%, compounded annually. Then that one, then if you want to find out how much money you'll have, you just can plug it into the formula. Let's say we're going to leave it for 10 years. So A sub 10 is going to be P, which is $10,000, okay, times 1 plus 5%, which is my R, which is 0.05 to the power of 10. So $10,000, okay, times 1.05 to the 10th power, and when we calculate that, that will tell us how much money we'll have at the end of the 10th year, compounded annually. Now, sometimes you get compounded semi-annually. So let's take a look at that formula. So we have a formula, A sub n is equal to P times 1 plus R to the n. So if you get interest that compounded semi-annually, for example, let's say you're getting 10% interest. R is equal to 10%. Okay, and when I say compounded semi-annually, that means twice a year, but they don't give you the whole 10%. Okay, twice a year. They give you basically, because this is for each year, so they'll give you like 5%. Okay, the first 6 months, and then they'll give you the 5% rate in the second 6 months. So basically, semi-annual means you're going to divide that by 2. So if you're going to get compounded, if you get compounded interest, let's say 4 times a year, then your rate is going to be 10% divided by 4. And if you do that 12 times a year, the rate will be 10% divided by 12. Okay, so Ben is equal to principal times 1 plus R divided by N, the number of times I'm going to compound that, and then N times T, which is T represents, the N represents the number of times you'll compound, the T represents time. So that's what my formula is. So I'm going to use a little mathematical trickerations here. I'm going to call my X is equal to N over R. Okay, so if my X is N over R, I can write this, okay, as same thing as P times 1 plus 1 over, okay, X. Okay, so if you look at this, that's if I write 1 over N over R, okay, which is this right here, okay, and then that really simplifies to R over N. So that is same thing as 1 over X. If I let my X equal to N over R. Okay, I'm also going to rewrite this N, so I'm going to solve for N, so my N is equal to X times R. Okay, so I can substitute that as X times R, and I have a T. Okay, as you can see, I'm getting close to PERT. Okay, now this is P, all that times 1 plus 1 over X raised to the power of X, and then that is going to be raised to the RT. Now if you were to take this function, just look at this one, y is equal to 1 plus 1 over X to the X. If you were to graph it, or if you were to just punch in numbers, let's say make my X 1,000, okay, or 10,000, or 100,000, or a million, if you keep going, keep changing numbers and calculating the value for that, this will end up getting closer and closer to 2.7182828459045 dot 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 dot. So we call, instead of writing all that out, we're just going to call it E. So therefore, okay, my A sub N becomes P, and this part now turns into E, and then I have RT. Okay, so this is known as a continuous growth formula. Okay, so we can write this, usually we write in calculus as y is equal to C, okay, for a constant, okay, E KT. Okay, these two formulas are the same thing. Okay, you write like this or this. Alright, so that brings us to actually doing a problem, an example, and let's pick problem number 2 as an example. Okay, it says John deposited $100, so that is your principal amount. P is equal to $100. Okay, and then the savings account pays interest of rate is 6%. Okay, 6%. And compounded continuously. As soon as you hear the word continuously, you have to go to A is equal to PERT. Anytime anything that grows continuously, you have to go to PERT, PERT. Okay. It says he just withdrew entire balance in the account. The balance was $200. How long was the money left in the bank? So what they're saying is he ended up having, the A ended up being $200. Okay, And then what they want to know, how long was the money left in the bank? Well, we're going to use our PERT formula. A is equal to P-E-R-R-T. So it goes in the exponent, E-R-T. So A is $200. How much we have left? Okay, we start out with $100. Okay, and then you have E, and R is 6%, which I have to convert that to decimal point 0.06, and then we have a T. Now we have to solve for T, because that's asking us how long it took $100 to turn it to $200. Of course, we're going to divide by 100, so we're going to get 2 is equal to E to the 0.06 T. Now, how do you solve this? So we have to ln both sides. So I'm going to have ln of 2 is equal to, when I ln the right hand side, the E is going to go away from me. I'm going to get 0.06 T. So what's my T? T is equal to ln of 2 over 0.06, or if you want to clean this up, this is going to be ln of 2 over 6 over 100, okay, and that is same thing as 6 times ln of 2 over 100, or you can reduce this to a 3 and a 50, so 3 ln of 2 over 50, okay, and this is your time, okay. Of course, you can punch in your calculator, find out what ln of 2 is, and come up with the decimal representation. Okay, that's number 2. So let's go to number 6. Okay, this is problem number 6. Okay, and that was on section 43, but this is section 44. Okay. Alright, section 44, number 6. For a certain bacteria to grow, the growth constant is, when they tell you growth constant, they're really telling you R. Okay, or in this case we'll call that K, and that's going to be 0.745. When time is measured in hours, how long will it take for 2 bacteria to increase to 1,000? So the C is what you start out with this 2, okay, and then the amount you're going to end up with, which is your Y, is going to turn out to be 1,000. Okay, so we're going to use this formula. Y is equal to CEKT, same thing as PERT. I'm going to plug in all the numbers I have. I want the bacteria to go to be 1,000. I'm starting out with 2 cells, okay, and I have an E, and K happens to be, that's my growth constant, or the rate of growth, is 0.745, and T is what I'm trying to find. Of course, when I divide by 2, I got a 500 is equal to E to the 0.745 T, and I'm going to ln both sides. I'm going to have ln of 500 on the left side is equal to 0.745 T, okay, and then I'm going to divide. Both sides are 0.745 T, so my T is equal to, okay, ln of 500 over 0.745. Since they told me these are hours, I have to put in hours. 60,000 rabbits. And then it states that in 1867, okay, the rabbit population increased to 2,400,000. Okay, assuming the number of rabbits grew exponentially, okay, what that means is, growing exponentially means we're going to have, since it's a continuous growth, we're going to use Y is equal to CEKT. Remember, this used to be A is equal to PERT. Okay, so K and the R are the same, and P and the C are the same. That's the initial amount. So, having said that, let's go to the question. It says in 1870, how many rabbits do we have? Okay, we want to find out how many rabbits we have. So that means we've got to build a mathematical model using this formula. Okay, so let's plug in information that we have right now. Okay, we know we start out with, okay, C, which is 60,000. Okay, and we also know that the rate, well, no, we don't. So we'll call that proportionality constant T. But we also know that from 1865 to 1867, that's 2 years. So 2 years later, okay, this thing turns into 2,400,000. Okay, so now we can solve for that rate of growth, or we call that proportionality constant. So when I divide both sides by 60,000, the 4 zeros here cancel out, 4 zeros there cancel out, and then divide by 6, that's going to give me 40. Is equal to e to the 2k. Of course, if I want to solve for this, I'm going to have to ln both sides. ln of 40 is equal to 2k, and my k is equal to ln of 40 over 2. So we're going to now, we have our equation. Our equation looks like this. Y is equal to 60,000, okay, and we know what our k is. K is ln of 40 over 2 and times time. Okay, now we have our mathematical model. We need to predict the future. So what the future is what happens here. So this took 2 years. So from 65 to 70, that's going to be 5 years. So we want to find out what happens when t is equal to 5. So we're going to substitute that in. So we're going to have y is equal to 60,000, okay, e to the ln of 40 over 2 times 5. Alright, once we calculate this right here, okay, that turns into y is equal to 60,000 e to the 9.222, and when we raise e to the 9.222, that turns into 60,000, okay, times 10117.279. And then when we multiply that out, my y turns into 607, comma 036, comma 719.9. But I can't use the 0.9. I can't round up the rabbits. Okay, unlike money, I cannot round up the rabbits, so I have to cut it off. And so my answer is 5 years later. It's going to turn out to be, okay, 607,036,719 rabbits. Alright, that is it.